Hello everybody. Today I'm not streaming, I'm not programming. Rather, I want to inspire from Khan Academy. I want to do a series of videos on reinforcement learning. Ideally, it will start from like the super introductory basic stuff on reinforcement learning and end up discussing about why reinforcement learning is so important. Today, especially in how large language models are fine-tuned through reinforcement learning, and how and why we choose reinforcement learning to do that. So I want to start by doing a mathematical background of reinforcement learning because I think that it's really important to understand what it is essentially. Like you can read the papers, you can go through the algorithm, you can write it in PyTorch, but you need to know the mathematics in order to understand what is going on. And so reinforcement learning is a very simple thing. The goal of reinforcement learning, let me write over here. So we have the title here, and the goal of reinforcement learning is to optimize. You will hear me repeat many times. This is also something Khan Academy does. This is because talking and writing is very difficult at the same time. Optimize what we call Markov decision processes. Markov decision processes. Doesn't fit. Processes. And so these are called MDPs for short. And what a Markov decision process is you have a Markov chain, which is a random process. A Markov decision process has the added property of having an agent that is able to make decisions. You might know agents now from AI and large language model agents and AI agents. This is not that. This is more true to what an agent does. An agent is a decision maker in this situation. Reinforcement learning agents are travel through a graph essentially. So let's have a simple example. We have here the start state. I mean, any state can be the start state, but like, let's say that here is the end state, and let's give them names. So this one, let's add some middle states also. Let's add 3, just for, it's going to be messy. Let me actually give me some extra space here, and here. And so we have the capacity from the start state to go to each of those. And then from those, we have the capacity to go to each other. Let's make a simple process. Let's make it so that they can go only to the nearest neighbor. And so we have here this thing. I forgot this here. And from this state we can go here, and from this state you can go here. And so let's name the states. So this is the state 0. This is state 5. 0, 1, 2, 3, 4. So let's state 4. And these are state 1, state 2, and state 3. And now we have the following. These are the states. So to begin with, we have a Markov decision process is a space this more like a P. MDP is a space, a mathematical space, where we have the following. It has a set of states. So S0 to S4 is the state space. We have the action space, where the actions are the arrows. So from S0 to make the choice to go to S1 or S2 or S3, and from S3 to S2 or to S4, etc. We also have the transition probabilities. So at each moment there is a probability that from S0 we will go to S1, and this is the probability P01. We also have likewise P02 and P03. We also have probabilities between the two. Let's say that they are equal for simplicity. So we have P23 and P12, and we also have P14, P24, and P34, and also we have a reward. So we have what is called a reward function, either written as a small r or written as a big R because it's a function. I prefer a small r, and this is the reward given for the choice made on the action. So if we go from here, we have like this is the reward 01, reward 02, reward 03, reward 2, 3. Let's say these are equal also both ways. So R32 is the same as R23, R12, R24, R14. We're filling the blanks now, and R34. I hope I haven't forgotten any. So an MDP is a mathematical space with S, the state space, the action space, the transition probabilities, and the reward function. And we also have gamma, which is discount factor. A discount factor becomes clear very soon as to why it exists. So the goal of reinforcement learning is to optimize the Markov decision process. And specifically, what that means is that we won't find a policy given symbolized by pi. So find pi such that we have the maximum of the following, and the following is that we want to maximize the reward, and the reward is given as a function of the state and the action. And so if we go to S0, we have 3 possible actions to go to S1, to S2, or to S3, and each action is associated with a reward. So the S0 to S2, the reward function given S0 and the action to go to S2 yields R02. And so that is the reward for that time step. And so we want to maximize this function for the entirety of the Markov decision process. And the way that we talk about the entirety of the Markov decision process rather than a specific reward is to take the sum over all possible steps, symbolized by t, over all time steps, because this is a process. So you go from S0 to S2 and then you cannot go back, so you have to choose between S1 and S4 and S3, and then you have to pick another action until you end up at S4. And so because you can end up in a loop where you go to S2 from S2 to S1 infinitely many times, if R12 is the biggest one and the policy you try out is the one that says go from S2 to S1 and from S1 to S2, then you end up having that the sum diverges to infinity if R12 is bigger than 1. And so we have also gamma to the power of t, where gamma is less than 1, usually 0.9 or 95 or whatever. And to do this, to finish what the actual thing that we try to find is that we want to take the expected value of the sum. So the integral, or however you want to say, and this we symbolize with Q P star, is defined as the maximum of this. And this is reinforcement learning. This is what we're trying to do. We're trying to maximize the expected sum of rewards over a Markov decision process. That's the entire thing.